Language modeling has seen significant advancements over the years. In the last decade, major breakthroughs include the introduction of neural networks for text representation, such as word-to-vec and n-grams in 2013. In 2014, sequence-to-sequence models like RNNs and LSTMs improved performance on NLP tasks like translation and text classification. By 2015, the focus shifted to attention mechanisms, leading to the creation of transformers and their numerous variants. In this video, we're going to crack open the magic behind transformers. Don't worry, not the kind that turns into robots, but the ones that turns messy, confusing text into pure genius. We'll be diving deep into how these models work their magic. So let's get started. Transformers were introduced in the groundbreaking 2017 paper, Attention is All You Need. Prior to this, earlier models could represent words as vectors, but these representations lacked context. The meaning of a word often changes based on the surrounding text. For example, the word bank in riverbank and bank in bank robber might have been represented by the same vector in older models, which didn't account for the different meanings of the word in different contexts. This is where transformers and attention mechanisms revolutionized the field. At its core, a transformer is an encoder decoder model that utilizes the attention mechanism to understand context better. Its architecture allows for parallelization, meaning that it can process large amounts of data more efficiently than previous models such as RNNs and LSTMs, which process data sequentially. The attention mechanism is crucial to transformer success, as it allows the model to focus on different parts of the input simultaneously, significantly improving tasks like machine translation and text generation. A transformer consists of two main components, the encoder and the decoder. The encoder processes the input sequence, refines its representation, and passes it to the decoder, which generates an output based on the given task. The encoder is made up of multiple identical layers, each contributing to better and more refined input representation as the data moves through the stack. In the original research paper on transformers, the model is built using a stack of 6 encoders. However, this is not a fixed number. It's a hyperparameter that can be adjusted depending on the task or model complexity. Although each encoder in the stack has the same structure, they are trained with different weights, allowing them to capture various aspects of the input data. Each encoder consists of two main sublayers. The first layer is called the self-attention layer. Self-attention allows the model to focus on different words in the input sequence, helping it understand the relationships between words, regardless of their position. This enables the transformer to capture dependencies across the entire sequence even if the words are far apart. The output from the self-attention layer is then passed to a fully connected feed-forward neural network, which is the second layer. This network processes each word independently, but it uses the same set of parameters across all positions in the sequence. This ensures consistency while improving computational efficiency. The decoder follows a similar structure with two sublayers, self-attention and feed-forward. However, the decoder also includes an additional encoder-decoder attention layer, which helps it focus on relevant parts of the input sequence generated by the encoder. This layer allows the decoder to produce context-aware outputs based on the encoded input sequence. Before we dive into the details of the self-attention mechanism, it's essential to first understand word embeddings. In transformers, input words are transformed into dense vector representations known as embeddings. These embeddings map semantically similar words closer to each other in a high-dimensional space, allowing the model to better capture meaning. However, the position of each word in a sentence is also crucial for understanding context, which is why transformers employ positional encoding. Since transformers process all tokens simultaneously, positional encoding is crucial to preserve word order and maintain meaning in sequences. Once the words in the input sequence are converted into embeddings, each embedding flows through the encoder's two layers. First, the self-attention mechanism processes the word at every position. Think of self-attention like this. In the sentence, the animal didn't cross the road because it was tired. The model uses attention to ensure that it refers to the animal and not the road. This process helps the model correctly interpret the relationship between words. After self-attention, the embeddings are passed to a feed-forward neural network. Here, each word embedding is processed independently by the same network. Unlike self-attention, where dependencies exist between different paths, the feed-forward layer operates without these dependencies, allowing it to process multiple paths in parallel for greater efficiency. Let's take a deeper dive into the self-attention mechanism and understand how it works step by step. Each word in the input sequence is first converted into a dense vector, capturing its meaning in a high-dimensional space. The model then generates three new vectors for each word by multiplying these embeddings with three learned weight matrices. These vectors are known as the query, key, and value vectors. The purpose of these vectors is to help the transformer decide how much attention each word should give to others in the sequence. The query vector represents the current word, the key vector represents the surrounding words, and the value vectors contain the actual information to be shared between words. Next, the model calculates attention scores. It does this by comparing each query with all the keys in the sequence. This comparison results in a score that indicates how relevant one word is to another. For example, in the sentence "the cat sat on the mat," when the transformer processes the word cat, it checks on how much attention should be given to other words like sat or mat to capture their relationship. The scores indicate which words in the sentence are most related to the word being processed, allowing the model to form connections between distant words. Once the attention scores are computed, the next step is normalization. These scores are first scaled by dividing them by 8. This is because the dimension of the query and key matrices used in the transformer papers are often 64, and the model divides the product of these matrices by the square root of their size. This helps in stabilizing the gradients and ensuring that the scores do not get too large. After scaling, the scores are passed to a softmax function, which converts them into probabilities, ensuring that they sum up to 1. These probabilities indicate how much focus each word should give to other words in the sequence. Finally, the model multiplies these probabilities with the value vectors. The value vectors carry the actual information of the words. By weighing these values according to the attention probabilities, the transformer generates a new representation of the word that incorporates context from the entire sentence. This output is then used for further processing, whether it's for translation, text generation, or any other task. This process is applied to every word in the input sequence, allowing the model to understand the relationships between words and build a context-aware representation of the entire sentence. Through this mechanism, transformers can capture long-range dependencies and produce more accurate, meaningful outputs. In the actual implementation, however, this calculation is done in matrix form for faster processing. The first step is to calculate query, key, and value matrices. We do that by packing our embeddings into a matrix X and multiplying it by the weight matrices we've trained. Finally, since we are dealing with matrices, we can condense all the steps into one formula to calculate the outputs of the self-attention layer. One self-attention operation often isn't enough to capture all the intricate details within a sentence. And that's where multi-headed attention comes in, a clever enhancement introduced in the original paper. Instead of performing a single attention calculation, the transformer generates multiple sets of query, key, and value vectors. Each set focuses on different aspects of the sentence, allowing the model to capture a wider range of relationships. After computing attention scores for each set, the results are combined and passed through a final weight matrix to produce the output. This process enables multi-headed attention to simultaneously focus on different parts of the sentence. For example, one attention might focus on the subject, while another head zeroes in on the verb, ensuring a comprehensive understanding of the sentence structure. Finally, after concatenation, we multiply them by an additional weight matrix because the feed-forward layer is not expecting 8 matrices, and rather, it's expecting a single matrix. To recap, we start by embedding the words in our input sentence. Next, we calculate the query, key, and value matrices. Then we apply multi-headed attention by performing multiple attention calculations in parallel. After that, we concatenate the resulting matrices, which gives us the output matrix that has the same dimension as the input. This process ensures that the model captures a rich understanding of the sentence, focusing on different aspects all at once. That's essentially the primary mechanism behind how transformers function. There are additional components like positional encoding, residual connections, and predictions on the decoder side that we will now discuss. One aspect that hasn't been covered in the model so far is how it accounts for the order of words in the input sequence. To address this, the transformer incorporates a vector into each input embedding. These vectors adhere to a specific pattern that the model learns, enabling it to determine the position of each word and the distance between different words in the sequence. The underlying idea is that adding these values to the embedding creates meaningful distances between the embedding vectors when they are projected into query, key, and value vectors and during dot product attention. Following the attention mechanism, the output is passed through a feed-forward neural network that processes each token independently. Transformers also incorporate residual connections and layer normalization to help prevent information loss and promote stable training. Residual connections enable the model to retain the original input information by adding the input back to the output layer. In contrast, layer normalization helps prevent the model from becoming biased towards extreme values, thereby enhancing learning efficiency. Having covered the key concepts of the encoder, we can now understand how the decoder operates as well. Let's break down how these components work together. The encoder processes the input sequence first. The output from the final encoder layer is transformed into attention vectors, which are used in the decoder's encoder decoder attention layer. This enables the decoder to focus on the relevant parts of the input sequence. The decoding process repeats in step until a special token signals completion. At each step, the output is passed to the next decoder layer, similar to how encoders handle their outputs. Like with the encoder inputs, decoder inputs also undergo embedding and positional encoding to track the position of each token. In the decoder, self-attention is restricted to earlier position in the sequence, achieved by masking future positions before applying the softmax in attention. The encoder-decoder attention layer operates similarly to the multi-headed self-attention, with one key difference. It generates queries from the current decoder layer while using the keys and values from the encoder's output. Once the decoder stack generates a float vector, the challenge is converting it into a word. This task is handled by the linear layer followed by the softmax layer. The linear layer is a dense neural network that maps the decoder's output to a large vector known as the logits vector. For instance, if the model has learned 10,000 distinct words, the logits vector will have 10,000 elements, each corresponding to a word's score based on the model's training. This vector is what the linear layer produces. The softmax layer then transforms the scores into probabilities, ensuring all values are positive and sum up to 1. The word linked to the highest probability is chosen as the final output for that step. Now that we have gone through how a trained transformer performs a forward pass, let's briefly explore the intuition behind training the model. During training, the model goes through the same forward pass. However, since we have the labeled data, we can directly compare the model's predictions to the actual correct output. For instance, imagine our output vocabulary consists of just 6 words: A, M, I, thanks, student, and end of sentence. The output vocabulary is defined during the pre-processing stage before the training begins. Once this is set, we can represent each word in the vocabulary using a vector of the same length in a process called one-hot encoding. For example, the word M can be represented by the following vector. With this foundation, we will then focus on the model's loss function, which is what we aim to optimize during training to achieve a highly accurate model. When training a model, such as translating mercy to thanks, the goal is to produce a probability distribution that correctly identifies thanks as the output. However, in the first step, the untrained model generates random probabilities due to its initial weights. The training process involves comparing the model's output distribution to the correct one and using backpropagation to adjust the weights, gradually improving accuracy. For longer sentences, the model outputs successive probability distributions, each representing a word. The final distribution should have the highest probability for I, the second for M, and so on, until reaching the end of sentence token. Training refines these distributions over time. Greedy decoding selects the word with the highest probability at each step, while beam search considers multiple possible sequences to find the best translation by keeping track of top hypotheses. We will look at different decoding strategies in a different video. Softmax, after that, helps by distributing some probability across all words, aiding the learning process. In conclusion, transformers have transformed natural language processing through their attention mechanisms, multi-headed attention, and the encoder decoder architecture. They provide substantial advantages over earlier models like RNNs and LSTMs by facilitating parallelization and effectively capturing long range dependencies in the text. In upcoming videos, we'll delve into specific applications of transformers, including GPT, BERT, and T5, to understand how these models drive some of the most advanced NLP systems worldwide. Thank you so much for joining me today. If you found this video helpful, make sure to subscribe, hit the bell icon, and like the video. Feel free to drop a comment with your suggestions or questions. I'll see you in the next video. Have a good one.